Okay, let's start with our first question. Find the area or express the area via integrals. In part A, we have a curve like that. This curve is in terms of phi, so it's like, let me put it in this way. So it's like when your x is x and y like that. So it's like a parabola like this. Okay. So to be able to find its intercepts in y-axis, we need to equate x equals 0 because x equals 0 is y-axis. So 0 is equal to y minus 1 squared minus 1. So y is equal to uh, plus minus 1 plus 1. So it is uh, 0 and 2. Okay. So my parabola is like this. So this is 2, this is origin, this is x-axis, this is y-axis. Okay. What about this curve? This is like y equals 1 minus x. Just consider minus x first. It's like a curve with negative slope. And you just push one, shift one unit to up. So it's like, okay, we can also understand this y-axis intercept. So we put x equals 0. So you get y equals 1. So it's like that. Okay, the region between them is here. Of course, this region is also between them, but we are looking for a finite region. Okay, okay. So now we can denote this area by an integral, but we need to understand this boundary. The one of the boundaries is okay, 2, y equals 2, and no, not 2. 2 is here, 2 is here. So we need to understand this point also. So what do we do is uh, intersect these two curves. I mean, write one of them in the other one. So we can do it like that. X equals to y equals to minus 1 minus x. So x equals to 1 minus y square, x equals to 1 minus y. So I'm just rewriting this equation minus 1. So instead of 1 minus y or y minus 1, I can use x, so it's like x squared minus 1. So x squared minus x minus 1 equals to 0. So I get what? So I need to solve this. So b squared minus 4ab. So it's like a AC. What are A, B, C? A is here, 1, B is minus 1, C is minus 1. So this is like 4. Okay, B is 1, so 1 plus 4, it's like 5. So my roots are, but they will be in terms of x. Not good. Nice. Anyways, so it's like uh, 1 plus minus square root of 5 over 2. Okay, you can also find the y-intercepts. What do you do? What do you do is just put one of the equation because they are in the both curves, these 2 points. And maybe we can use this thing. When you put x here, you get, uh, we are going to add, okay, 1 minus x, 1 minus 1 minus plus square root of 5 over 2. Now it is 1 minus plus square root of 5 over 2. Right? Nothing is changed actually. Yeah. So it's like 1 minus square root of 5 over 2. 1 plus square root of 5 over 2. I'm gonna write in terms of y. So with respect to x, which curve is the upper one? This curve is the upper one, right? Upper curve, lower curve. So, and this region is simple because perpendicular to y-axis, I always come from this left one or lower one to upper one, right? So this is simple region. Okay. Sometimes we draw arrows. Okay. So my integral is x equals to some equation. So 1 minus y minus the lower one is y minus 1 square minus 1 dy. Okay, should give me the area between these two curves. What about part B? Bounded by the parabolas y equals to 2x and this other one. Okay. Can we have factorization? Maybe if I can write this like that. No, it's not also not obvious. But do we have a root? Let me check. Again, b square minus 4ab should be positive to be able to have a root. But do we care about roots? Yeah, we don't care about roots because we only care about the roots of the intersection. So let's intersect. But before that, maybe let's try to draw the curves. Uh, because I know that this will be some inverse parabola. Okay. I don't know the place, but it's like something like that. Okay. Then 2x square will be like that. And if I can find this intersection, okay, I can find this region between them. Okay. Okay, let's solve that. 2x square equals minus x squared plus 3x plus 6. So 3x squared minus 3x minus 6, or in terms of 3, in parentheses of 3x squared minus x minus 2, 0. This can be factorized. X minus 2, x plus 1, right? Minus 2 plus 1. That's correct. So this will be minus 1. This will be minus 2, plus 2. X equals 2, x equals minus 1. So integral in terms of x from minus 1 to 2. What is the upper curve? This inverse parabola. Minus x squared plus 3x plus 6 minus 2x squared dx. Okay, this will be giving me this area between these two curves. Let's also solve. Let me copy and paste another question. Hmm, okay, we have two curves. We have a region between them. We are going to rotate this region around the x-axis and we will express. Okay, so let me calculate. This is an inverse parabola. This has root 2 minus x, 2 plus x. So it's like 2 and minus 2. And this is like a line x equals to y, but it is shifted 2 upwards. Okay. Yes, like that. And this is 2, this 4, because when you put x equals to 0, this is 4. So we are looking for this region. So we are going to rotate this region around the x-axis. Okay, around the x-axis. Okay, just look at the region above x-axis first, then also rotate this, but there will be some intersection, right? Okay. But do we care about this? Not at all, because we will just take this difference, okay, and we will rotate this disk, for example. Okay, let's take this little thing. When you rotate it, uh, I mean, do we take some extra rotation after this? I don't think so. I don't think so. Uh-huh. Okay. Because let me draw it more carefully. Okay. So let's take this. If you rotate around this x-axis, uh, if this upper part is bigger, you will take another extra term. But yeah, it's no problem. So we can just apply the formula. So what is the revolution by a disk method? So it's like from A to B, whatever this interval. So pi f of x square minus pi g of x square dx. So this is upper, so this is lower. Okay. So let's calculate this integral then. So let's find the intersection first, because both are y, right? So they need to satisfy these 2 points. Sorry. So plus 2 minus 1. So it's like plus 2, x minus 1. So it's minus 2. So this is 1. My integral is from minus 2 to 1. Let me take this pi in front. What is the upper part? Upper part is this inverse parabola. Square minus this lower line, I mean line, dx. Okay. Mhm. Let me find another question. Let me copy and paste some classical one, actually. Mhm. Let's calculate the um, volume of a torus, for example. Okay, let's volume of, or it was an exercise problem, volume of a sphere, or uh, region bounded by sphere. So what do I mean is consider a sphere like this. We are going to find the volume of it. Volume. Let us say this radius is r. Okay. First, I only have one variable, calculus. So I need to make some circle, right? Or half circle. Then I'm gonna find the region. When I rotate it, I'm gonna find the uh, volume of the sphere. So it's how to construct. So consider some half circle. Let me call y is equal to square root of. And since the radius is r, let me call this is r. So it is like r square minus x square. Right, because when you open it, it will correspond to x square plus y square equals r square, which is a circle. R at the center 0, 0. If you also take the minus one, it will give you the lower part of the circle. Hmm. Now, what I need is, I'm gonna calculate this region, not calculate, but determine. Then when I rotate it, what do I have? I would have some volume of a sphere. Okay. Now it is like from 0 to r pi this equation's square dx, or 0 r pi x square square dx. So it is 0 to r pi r square minus x square dx. Now this r is constant, right? This is a proper integral, continuous function, and boundaries are close and bounded. So pi and open. What is the integral of r squared? It is r squared x. What is the integral of minus x cubed? X squared. It is like x cubed over 3. And the boundaries are 0 and r, which is equal to pi r cubed minus r cubed over 3 minus pi, the other boundary. When you put 0, everything is 0, so you get 0. Let's calculate this. It is like 3 minus r cubed is like 2 over 3 r cubed, right? There must be something. Because volume of a sphere is 4 over 3. Anyway, let me calculate it. So it is like pi 2 over 3 r cubed. But it shouldn't be. So we made a mistake. Ha, my mistake is the boundary. Okay. Because if you write your boundary is 0 to r, it means that we are only calculating this half thing. So I need to calculate to 0 to 2r. Okay, so it should be 2R. So this whole calculation is correct, but the volume, if this is called I, then volume is 2I, which is 2 over 4 over 3 pi r cube, as always. Okay. What I did was the taking the half of the boundary, so not the all. Okay. Now we are fine. We can similarly calculate the volume of a torus. Consider a torus like this. Torus in Turkish means simit. Okay, a donut. Let's calculate the volume of a torus or donut. So the way of thinking this as follows. Consider a coordinate axis. Take a circle, and this circle shouldn't be in this axis. It's like away from this axis, so that when you rotate it, right? So we will have a region. When you rotate this region, you will have some, donuts, right? This will be, so it will give me the volume of a torus or volume of the region bounded bounded by a torus. Now we can also calculate, I hope, because sometimes some integrals are not calculatable or whatever it is. So take a circle, okay, at the center A and B with radius R. Now take bigger R now. There is no difference. Okay, take little r. Take little r. So this is again y axis x. What's the definition of this circle? This is like x minus a square plus y minus b square equals r square. So in terms of y, it's like y equals to square root of course, we will have two parts, plus and minus r square minus I will have I will need bigger. Okay, r square minus x minus a square plus b. So plus one will be upper one. So this will be lower circle, half circle, half circle. Okay, this will be like upper. This will be lower. Anyway, so let's calculate. So again, this method. So I'm gonna have the region will be bounded by these two things. Okay. I will calculate the full thing, which will give me a cylinder, a bit interesting cylinder. Now I will subtract this lower part, subtract this part. So integral is, um, okay. Now let's not make the same mistake. My center is A, so this part is x equals to A. Okay. So now this part is A plus R. This part is A minus R. So I'm gonna take the integral from A minus R to A plus R. My upper circle is, let me take the pi's, let me call wall torus. The upper part is this one. So square root of r square minus x minus a square. Let me write it more clearly. minus uh, square minus x minus a square. This will be negative plus b square dx. Okay, let's try to calculate. Maybe it is easier. Okay, this is r square minus x minus a square plus b square minus stay plus 2b square r square minus x minus a square. This will be the similar r square minus x minus a square plus b square minus 2b square. Ah, this will be minus, they will be cancelled. So this ugly squares will be cancelled out. Minus a square. Uh, Not so much because we have extra minus here. So this will be a hard one. Pi a minus r a plus r. But I'm gonna leave it as an exercise. Okay, this will be cancelled. Okay, and we will have 4b squared of r square minus x minus a square dx. Okay, let me give you a hint about solving this. Let's make the substitution. Subs exercise. And let me give you the hints. Substitute uh, x minus a as r sinus. Oh, okay. Now dx will be r is a constant, use a variable cosine u du. And this integral will be, and also change the boundaries. Okay, when x is equal to a minus r, sorry, it will be minus r, right? When you put this here, not so much. Arctangent minus 1, something like that, right? Because put x equals to a minus r, so you get minus r, divide each side by r, you will end up with minus 1. So take the arctangent, u becomes arctangent, not tangent, sinus, minus 1. And above, similarly, when you put plus 1, you will have arcsinus 1. But we know what is arcsinus 1, right? It will be pi over 2. It will be minus pi over 2, etc. So inside the 4p and r squared 1 minus sin square u. And instead of the x, I have r cosine u day. And this integral will be, solvable. Okay, you can solve it and calculate the volume of a torus. Now we can also calculate a lot of things using these ideas. But let's calculate also some lengths of curves and surface areas. Okay, or before that, maybe one more classical example. Okay, let's try to solve this question. I'm not sure. Let's say this will be our last volume question. Bounded by the curves y equals to 2 cosine x 0. Oh. Let me draw this via some program. Okay, since we are online, 2 cosine x, 2 cosine x, cosine x, cosine x, 0, x equals to 0, x equals to pi over 2, x equals to pi over 2. Mm, okay, let me just show you this region. Print screen, okay. Okay. Now, this above one is this red one is y equals 2 cosine x. And this below one, blue one, is y equals cosine x. And this is x equals to 0. This is x equals to pi over 2. Okay. So what is this region we are talking about? And this is this region. Okay, this is not a good color. Huh, let me try blue one. This is what we are talking about, okay? So first, what is the area between curves? Even though it is not in the question. So it is like from 0 to pi over 2, 2 cosine x, x cosine x, dx. So it is like integral of cosine x, okay? Because both curves are the 2 cosine x and cosine x. So what about this revolution? So what was the rotation axis? Let me check. About the line. Ha, okay. There is some error that we made. This region is not, okay. I can change it. Okay, bounded by this, and this, and about the line minus pi over 2, whatever. So we are going to rotate it around this axis, x equals to minus pi over 2. I changed the question a bit because I misread it. Uh, Sorry. So let's solve A. I'm gonna rotate this around this minus pi over 2. Okay. Here I can use, I don't know, not slice, shell method. Okay. Take a shell. Okay. I'm gonna rotate this shell around this axis. So this shell will be like that at each step, etc. So it will be a shell. Okay. What is the radius of this shell? Radius of this shell is from rotation axis to the point. But we are gonna take the integral from 0 to pi over 2, right? It is my bounded region. So this is 0 to this is my region of interest. So my integral is from 0 to pi over 2. So to be able to put also this rotation axis into the value, so I'm gonna add pi over 2. So my radius is okay before this integral, radius is x plus pi over 2. Okay. For each x, I'm gonna add pi over 2. That's my case. So what about this shell? This shell like this. So this dx. What is the height of this shell? Height of this shell is the difference of these two graphs, which is cosine x. What about the radius of x? It was x plus pi over 2. So this volume is, uh, when you cut it open, you will have this kind of longer shell, or the expansion of this shell. This is dx, so this is cosine x, and this length is 2 pi, the circumference of this circle with radius r. So it's like 2 pi r cosine x dx. Or I can rewrite as 2 pi 0 to pi over 2 x plus pi over 2, which is r, and cosine x and dx. Okay, this is your height, this is your radius, this is the term coming from circumference of a circle. So this is volume. By the way, this is not the disk method, this is a shell method. This is shell method. Now, let's do it by disk method. So to be able to do that as a disk method, I'm gonna again redefine everything. Since we are solving the different question other than the given one, I'm gonna rewrite it. Okay, this is my interest. So this is x equals 0, x equals pi over 2. This is my rotation axis. Rotation axis x equals minus pi over 2. Okay, a disk method. To be able to do that, I'm gonna work on the y coordinates because it will be perpendicular. So right. So my slices will be, this kind of things. Okay, this color is not good. Let me use this color. So my slices would be like that. To be able to write something like that, you need to write this as a x of some function, and that's x of another function. Okay, and as you can see, this region is not simple. Okay, because this is one of the simple region. Let me divide it by another color, for example, orange. So this is one simple region, first simple region, and this is second one. So I need to write two different integrals. In first one, the upper curve is this, lower curve is this. In the second one, upper curve is this, lower curve is this. Okay. So first, let us change the, okay, y equals 2 cosine x to x equals to something, some function of y, which is very easy. X is equal to arc cosine y over 2. Y equals cosine x is x is equal to arc cosine y. Now let's apply this method. Volume is equal to first integral. This is, let us also understand this intersection point, but this is very easy because this will be this, this is just y equals cosine x, and when x is 0, it is 1. So this height is 1. Okay, this height is 2. Okay, so in the first integral, the first simple region that I've written here, from 1 to 2, I'm talking about y's, and upper one is 2 cosine x, or here it is x equals arc cosine y over 2. So arc cosine y over 2 minus arc cosine y. No, not like that. square pi dy. Okay. Plus the second simple region from 0 to from 0 height, right? So this height is 0 to 1. So what is the upper one? Upper one is this. Ah, we we didn't write correctly this thing. Upper one is correct, but lower one is constant x equals 0, right? X equals 0, so it is 0 square. So sorry again. Okay, dy plus pi 1 0 to 1. Okay. Now I'm gonna write the same thing as I wrongly write in the first case. Arc square cosine y over 2 minus arc cosine y dy. Of course, I need to take square. Okay, this will give me the volume of the region in this method. As you can see, sometimes shell method is easier than the disk method. Okay. So this was a hard problem about this volumes. So let's go back, not back, forward to the length of a curve. There are something about rectifiable curves, etc. But we will understand. So my task is find the length of a curve in this region. So let me give you some pictures. This is a surface area. Not good. Arc length of ah, this is a good picture. Okay, if you have a curve like that, okay, if you have a curve like that, and you want to understand this length of the curve, you can first divide this curve into some line segments. Then if you take the summation of this line segment, you will end up with a number. And this number can be bigger than the actual length or smaller than actual length. Or is it correct? No, it is always less than the actual length because at each step you are taking the geodesic between two points. And the actual curve is at most this geodesic or longer. It means that you are always getting less length than the actual length of the curve. But if you take the limit, if you take the partition too much, okay, like infinitely many partition of a curve, of course the curve should be rectifiable. I mean, you need to make this process. So it's like the translation of it. Then you will end up with the actual length of the curve via an integral. Okay? But this is a curve in the space. Most of the cases we are only dealing with the curves that are given by a graph of functions. For example, in this picture, this is not a graph of a function, right? One point corresponding to two different points. So it's not a graph of a function in usual sense. So what we do is let's just focus of the graph of the curves. Okay. This is a function and this is a graph. Let me actually take the part A actual picture. What was it? ln secant x. ln secant x between 0 and pi over 4. Pi over 4. Secant x. Okay, this is the part A. This is part A. Part A. A. Y equals ln secant x. By the way, you don't have to draw the graph, right? But we want to understand what's happening. So at some, again, we don't know the formula, but we can derive. So assume that you have some function graph like this, as in this case, right? By the way, we are only concentrating on this part. We are only concentrating on this length of this curve. Okay, this is not in general because this is the boundary. Anyway, let's also focus on some boundary A and B. So we are going to calculate the length of this curve. What should we do? We should take an arbitrary x point or some dx. Okay, there is some corresponding part, but it will be some, slope. It is not always just horizontal. So I'm talking about wage terms because, yeah. So take a part of the length which is very zoom. You zoom, okay. You zoom it, zoom, zoom it, zoom. Okay. Now this let us call ds. If we take the integral from AB of ds, then it will be length of the curve. Okay. But this dx has a slope, right? And it has a parts of dx and dy. Now, or delta. Let us call delta. Delta x, delta y. Okay. Delta s square is equal to delta x square plus delta y square. Okay. By the way, we can calculate this delta x square root of 1 plus delta y over delta x squared and delta x. Okay. So now it's like before this integral, we have some limits. Uh, delta x is going to be small. In summation, square root of 1 plus delta y, delta x, delta x. Okay. When you take this limit, so you will end up with this integral. In this case, this ds would be 1 plus y prime square dx. Okay. Of course, there are some details to be filled in. You need to take an arbitrary partition or some specific partition. It's like this electric potential question in the exam. But it's like geometry. I want you to understand unofficial, okay? But intuition. Unofficial intuition approach. Okay? Because you don't have to, write everything when you solve it. But this thing just gives you the intuition when you approach to a problem. So this is the formula of a length of a curve. When curve is given by a graph of a function. Okay. Now, in this case, let us apply it. Our case is from 0 to pi over 4, 1 plus ln secant x primes square dx. What is ln secant derivative? D over dx ln secant x. Okay, just recall the rules of ln, right? So what is the derivative of secant x? Okay, secant x is just 1 over cosine x. Take the derivative of each side is like minus minus sine x, the derivative of cosine x, over cosine square x. So it's like secant tangent. So secant x tangent x. Right. So you need to take the square of it, sum with 1, and calculate this integral. Let me call it L. So L is equal 0 by 4 square root of 1 plus secant square x tan square x dx. Can we calculate this integral easily? By the way, it is not correct because this is only the derivative of inside. You need to also divide by secant x. So it's like tangent x. The derivative is just tangent x. So there is no secant. Uh, okay, there is no tangent. There's no second part. So it's like 1 plus tangent x squared dx, right? Because this is the derivative of the function, you need to take the square. So it's like secant square, so 0, 5, 4. Since secant is positive in these boundaries, you can take it out, secant x, because this is secant square x. So dx, and we can calculate this. I'm not sure, it's like ln secant x plus tangent x. Something like that. I don't remember. Let's check it. When you take the derivative, check. When you take the derivative of this, you should I get secant x? Let's try. What's the derivative of this inside? Second derivative is secant x tangent x. The tangent derivative is secant square x divided by this thing secant, oops, secant x plus tangent x. Yeah, when you take into parentheses of secant x, there will be secant x. Secant x. So it's correct. When you put these things, you will find, okay, the length of the curve. You can also apply the similar thing to this thing. Let me copy and paste. Oops. Let me copy and paste. Hmm. Again, let me copy and paste the graph also. Y cube is equal to x squared. This is the graph of this. Okay. You can understand just like, okay. Because here y is equal to x to the power 2 over 3. The power is less than 1, so you expect some square root of x behavior in both cases because it's still defined on also negative x's. Anyway, we want to calculate it from -1 to 4. Okay, so we want to find this length of the curve. So just apply the formula, but you need to find the y prime. Okay. Okay. So it's like 2 over 3 x minus 1 over 3. So this is derivative of y with respect to x. If you take the square and put it into the formula, length of the curve is from minus 1 to 4 square root 1 plus 4 over 9 x to the power minus 2 over 3 dx. Mm, how can we solve it? Maybe you can change the variable. Mhm. Okay, let me understand. Zero, 3. Mm, no, you don't get anything useful. Maybe. Okay. Maybe if I consider, I don't know, x to the power minus 2 over 3, 9 as a, okay, or this thing as a tangent x, tangent u, okay? I mean, it will be 1 plus tangent square. Exactly. It will be like 1 plus tangent square u, then it will be secant. And what will be r dx? R dx would be, okay, these are not good. So let's take the d of both sides. 2 over 3 minus 1 over 3 x to the power uh, minus 4 over 3. It's like secant square u du. Okay. Of course, don't forget about dx. And we said that this thing is tan u, so we have dx minus 2 over 9 instead of, hmm, look, let me put minus 1 over 3. Instead of this thing, okay, I'm going to multiply and divide by it. Not actually. Okay. This is the fourth power. Okay. This is the fourth power. So it's like everything is mixed. 10u 3 over 2 10u is equal to x power minus 1 over 3. I want this thing, this term. So this is again 9. These are just constants and dx. So instead of x to the power minus 4 over 3, I'm gonna put fourth power of this. I hope I'm doing something not so bad. It's like an integral question. Here we have second square root. etc. Yeah, etc. You can solve this or just express it. Okay, this is my integral. Or maybe there's some mistake, but you calculate the integrals like that. I don't want to waste so much time on it. Maybe I'm missing something very trivial, probably, but I'm letting you to find it. So we have deal with lengths of curves. The only things that we need to check or we need to see is surface areas of revolutions. Let's also understand it. Okay, 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 okay. Okay, this is my question. Let me also give you the picture, which is very good. I find it. Okay. Now assume that you have a curve like that and you are rotating around x-axis. Okay, rotating around x-axis. So when you rotate it, this is the shape you get. You can either take inside and you get the volume of this shape or this only surface area. Okay? Surface area means that inside is empty. You are only taking the surface area. For example, surface area of a sphere is, surface area of a sphere. The sphere is like a surface. Not we are not talking about this three-dimensional shape bound by the sphere, but the surface of it. Okay. For example, torus is actually a surface, not a three dimension. Anyway, so how do we find this setup, but do not calculate, blah, blah, blah. Okay, we take, I'm gonna just teach the intuition because there you can also formalize it, but let's know, just understand. When you rotate a part of the curve, right? So let's say this is the part you get to rotate. So we have, let's say, delta x. Okay, this is delta x. But there is some corresponding, okay, around this delta x, you are rotating like this. Okay, something like that. So you have rotating something like that. Okay, rotating something like that. So there is some piece, right? You are rotating around this piece. So one of the piece is like that. Around on the surface, you have some piece, right? So this piece, or maybe use different color. Okay. So when you take this piece and cut it off from here, what do you get? You get some sheet or shell, but the shell has no interior. Okay. Okay. This is shell or the slit when you cut it off. So this is ds. Okay. When you talk about ds here or ds because they are symmetric because they are some ds and you have some length which corresponds to the radius, right? We have some radius here, r. We have r here, 2 pi r. So this length is 2 pi r. And r, in this case, is corresponding to the function's value, right? This r is function's value at x. Okay. Assume that we are considering the point at x. So this r is just f of x if you are considering y equals f of x. Mhm. So what is the area of this thing? So it's like 2 pi r ds. Finish. Or instead of r, you can put f of x ds if we are rotating around the x-axis. Hmm. Now let's solve the party. We have the graph ln x, so it's like this. Uh, Consider this region, okay? So I am rotating this curve, actually this part of this piece of the curve, around x-axis first. So what do I end up with is something like that, some curve like that, something like that. Okay, some curve like that, some surface. When you rotate around x-axis, this is the shape you get. It's empty. It inside is empty. So, by the way, I didn't write the formula, only the yes part. So this whole surface area is equal to whatever the boundaries you are taking from A to B, 2 pi f of x, and we have ds. We have already calculated ds in the arc length. This is arc length, by the way. Blank piece f prime x square 1 plus f prime x square dx. So this is the surface area formula. Okay. So here, um, what is my question? Okay, ln x. So surface area is from 1 to 3, 2 pi f of x, which is ln x, and ds, which is 1 plus, what is the derivative of ln x? 1 over x, the square dx. Okay. This is the surface area formula for this ln. Similarly, you can apply this formula for each function. Okay. You have 2 pi fx, which will correspond to each slit. And this ds is another function, right? This is square root of 1 plus f prime x squared, and which comes from the arc length of a curve. Okay, we cannot take just dx instead of this part. ds is not dx because it is not horizontal. That's why we need to consider these things. Okay, so that's all. We have deal with curves, volumes, shell methods, arc lengths, surface areas of revolutions, etc. Maybe if you like, we can also rotate this around x-axis to see what happens. Okay. Okay, let's rotate around y-axis. So now I'm gonna rotate this ds around y-axis. What do I have? I have this kind of thing. Okay, this kind of thing. So my shape will be like this. Okay, this will be my shape rotating around y-axis. It was rotating around x-axis. So now what is the surface area of this thing? So surface area. So let me call x-axis to y-axis. Surface area. So what is my boundary? When x is 3, ln 3 is ln 3. So this is 3 ln 3. I mean the height. So my integral would be, of course, would be in terms of y. That's why I'm checking this from 0 to y is 0, y is ln 3, 2 pi. So what is my function now? So it is like e to the power x, right? Y equals ln x means that x is equal to e to the power y. E to the power y, that's right, and 1 plus, what is the derivative of e to the power y with respect to y? E to the power y dy over dy. So e to the power y. Okay. E to the power y squared dy. Okay. This is the surface area when you rotate around y-axis. Of course, they are not the same because we are rotating through different axes. Okay. So that's all. Thank you.